All right, so today we're going to be talking about the second section in chapter 2, which is all about chemical reactions and enzymes. In your textbooks, which you can use if you need some help on the worksheet you're going to be doing today, you're going to find information from this section on pages 50 to 53. So basically, what we're looking at here is some very basic chemistry. We're going to talk a little bit about chemical bonds and what happens to those chemical bonds during a chemical reaction. We're going to talk about how energy comes into play from this whole process. And then we're going to connect it to biology by talking about enzymes. So let's do this baby chemistry introduction first. So chemical reactions are going to involve changes in chemical bonds. A chemical bond is a force that joins atoms of elements into compounds. So remember, we talked about monomers and polymers and all of the different elements that make up life's macromolecules. That's what we're talking about happening, is that in order to create those, they have to form a chemical bond. So this is a process where when we have a chemical reaction, we start off with one set of chemicals and then they become something new and different. In this process, they are going to conserve both energy and mass all throughout that chemical reaction. So some vocabulary that you need to know. We need to know about reactants and products. When we talk about photosynthesis and cellular respiration in their own chapters, these are going to be really important. So the reactants are what go in to my chemical reaction, and the products are what come out. We can use something called a chemical equation to represent what happens in a chemical reaction using letters, numbers, and symbols. When we write our chemical equation, we're going to put the reactants on the left side of an arrow, and we're going to put the products on the right side of that arrow. The arrow basically points to the products. So it shows what we go from to what we go to. We use it instead of an equal sign in math since we're in science and not math class. So here are two examples of chemical equations. I mentioned we are going to talk about photosynthesis and cellular respiration. So I figured let's go ahead and use these as two examples. So what we have here, we have our chemical equations. Reactants are on the left side. The arrow separates the reactants from my products. And I mentioned it points to the product side. So what I would like for you all to do, we're going to pause the video here. In your notes where you have these two equations, you are going to copy this information down. If there's something that is confusing to you, maybe wait on writing it down until you can come see me during a time later this week. I also want you to take this paragraph down here that explains what conservation is. Remember on the last slide, I talked about how chemical reactions conserve energy and mass. So make sure you have this note that talks about how conservation is when we're not going to create or destroy anything. We just take one thing and transform it into a new thing. So please pause this video here and restart when everybody is ready. In this slide, we're going to tie energy into reactions. So one of our vocabulary words from this chapter is activation energy, which you should have written down is the amount of energy required in order for a chemical reaction to occur. We have elements and compounds around us all the time, but unless the right energy is available, they're not going to react together. So energy can do one of two things. It can either be released or absorbed. So whenever we have these chemical bonds being rearranged in my chemical reaction, it's either going to be absorbing energy to create those bonds, or it's going to be releasing energy and most likely breaking bonds. So chemical reactions that absorb energy, you have to have some source of energy to start that reaction. You have to have some heat or electricity, or fire is usually something that we use. Think about fireworks by themselves. They're totally fine, but if they get too hot or if you light them, they explode. So that's an example of a chemical reaction. So a chemical reaction that absorbs energy is called an endothermic reaction. And the way that I can remember that is endo brings in energy. So it's spelled differently, but it sounds the same. On the other side of things, chemical reactions that release energy, they do not require an energy input. They happen completely by themselves. These are called exothermic reactions because in this case, the energy is making its exit out of the chemical system. So if we look at these energy absorbing, remember this would be an example of my endothermic reaction. We have energy on the y-axis and course of reaction. So basically this is just looking at time. We start with reactants and we end with products. So the activation energy required is going to be from the top of this, what looks like a little roller coaster hill, to whatever energy the reactants had. We have to have at least this much energy before the reaction occurs. Once we have that input of energy, then we're going to get some products out. Notice in my energy absorbing reaction that my products are higher up on my y-axis. This means products have more energy than reactants when I have my endothermic or energy absorbing reaction. The opposite is true in my exothermic or energy releasing reactions. So my products will be lower on the y-axis and they have less energy. Okay, so this is all well and good, Mrs. Vaughn. We know that you're a chemistry teacher, but we're in biology class. So let's bring this information that we just learned about chemical reactions, chemical bonds, and energy and talk about enzymes. So a catalyst is a substance that's going to speed up the rate of a chemical reaction. It does this by lowering the amount of activation energy required. If you have heard of a catalytic converter on your car, it's the same thing. So there is a chemical catalyst in that converter that helps decrease exhaust emissions. So that's why maybe this word sounds familiar to you. So catalysts in biology make life possible. So we have a class of proteins called enzymes that act as one of our biological catalysts to help speed up chemical reactions. If we did not have enzymes to help speed up these processes, things like digestion or breaking down different chemical compounds that our body needs to carry out processes like breathing, these processes would take way too long. And so the organism would not be able to survive. So if we did not have enzymes working the way that they're supposed to, organisms are not going to be successful and able to stay in life. So with enzymes, whenever we're naming them, we name them based on the reaction that it helps. And it's also going to end in the suffix ase. So if you ever see something in your reading and it ends in ase, A's, it is more than likely an enzyme. So as I mentioned, a catalyst is anything that speeds up the rate of reaction by lowering the activation energy required. That's all that we're showing here in this diagram. You have this diagram in your notes. So I want you to take two different colors or make one line really, really dark or dashed so that you can see that this blue line, this is the reaction pathway if there is not an enzyme. So we see this roller coaster hill is much taller than the red roller coaster hill. So between the red curve and the blue curve, the blue one requires much more activation energy. Well, we don't always have tons of energy available. So that's why, with the help of enzymes, we don't need as much energy and we can still carry out those processes even if we didn't have as much as we would require normally. The energy of the reactants and the products is not affected. It is just the energy that's required to carry out the process, which remember is called my activation energy. So it's great that we know now that enzymes work by decreasing activation energy, but how exactly does that happen? Enzymes work by providing what's called an active site. So think of an active site kind of like a construction site. We're going to bring together materials and build them in one place instead of trying to assemble these piece by piece by piece, all of these different places. So the reactants in an enzyme catalyzed reaction has a special name. They're called substrates. And a substrate and its enzyme have complementary shapes like a lock and key. Now, this is complementary with an E. If you tell somebody that you really like their shoes or you appreciate the hard work that they're putting into something, that is being complementary with an I. Complementary with an E means that one thing has a specific effect on another thing. So like a lock and key, they have to have the same shape in order for them to work. You can also have complementary flavors like peanut butter and jelly, strawberry and banana. So these are things that work well together because of this special arrangement. So we have my reactants, which remember we call our substrate. This whole other part, this light blue circle, represents my enzyme. And then this red line here represents my active site. So in a chemical process, the substrate is going to fit into the active site, kind of like a puzzle piece, and forms what's called an enzyme substrate complex. All that means is that the substrate is inside the active site of the enzyme, and this chemical reaction is taking place. After the chemical reaction is complete, my products are formed, they are released from the active site, and you notice that this is open and unchanged. This means we can reuse the same active site and the same enzyme to carry out the same chemical process many, many times as I have reactants available. So this is something that doesn't destroy anything. It just makes it easier to create my products. And then this diagram over here shows you a specific pathway that shows that in just a slightly different way. Remember, I mentioned ASE tells you that it's an enzyme. So we have an example here, carbonic anhydrase. ASE indicates that that is my enzyme. So this green thing represents my enzyme. The dark green section is my active site. It fits my substrates perfectly. They're converted into products, and then those products are released. If the substrates do not fit, the enzyme's active site will not accept them. So the only thing that should be going in an active site is the right substrates. So different enzymes are going to have different shapes for their active sites. There are a couple things that can affect the ability of an enzyme to do its job. The three that I want you to worry about in this class are temperature, pH, and something called regulatory molecules. So I'm going to give you an example of each of those. In human cells, the normal human body temperature, we've talked about a couple times in class, is about 98 degrees Fahrenheit. That's 37 degrees Celsius. So as long as I'm around 37 degrees Celsius, which is, again, normal human body temperature, the enzymes produced by human cells are going to work best at those temperatures. If I have a fever or if that temperature gets low for some reason, those enzymes aren't going to work. Remember, we've been talking about how if the temperature is out of that range of tolerance, we have difficulty surviving. So it all ties back in together. Similarly, enzymes in my stomach that help digestion happen to break down that food that I'm taking in so I can get energy and nutrients from that food. Those are going to work in acidic pH ranges because we have a strong acid in our stomach. So they have to be able to survive in that environment. If I eat foods that cause that pH to become too acidic or on the opposite side too basic, those enzymes aren't going to work as well. And then finally, regulatory molecules, they are kind of like the enforcers. So we have rules and regulations. You might have heard of that term before whenever you're playing a game or you're reading some rules like in our handbook. So regulations are rules. So regulatory molecules are kind of like the rule enforcing molecules. Basically, their job is to turn enzymes on or off. So the enzymes are being controlled by these regulatory molecules. They're not just working all of the time. That's it for our notes for today. If you missed anything, please check Google Classroom. These slides are available there. Remember, everything for me is always going to be under the classwork tab. I will be available for questions by email, but I cannot guarantee that I will be able to respond within the end of the class period. So do the best you can. Miss Savely is here to help you. What I need you to do now is work on worksheets. The front side is 2.3. It's a review from what we did before break. The back side is related to the information that was contained in these notes. So make sure you have those finished. And then if you finish early, there will be exit tickets posted online for 2.3. We're going to wait for 2.4, today's material, until Wednesday. Also, please make sure you turned in your vocabulary and completed the quizzes that was assigned prior to break. I'll be putting in lots of grades on Wednesday morning, including the exit tickets. So again, the 2.3 exit ticket, you need to make sure that you finish after you do that worksheet. Anything you do not finish in class is homework. The worksheet must be turned in before the end of class. Remember, textbooks are available in the lab. If you need them, please make sure to put them away neatly. As a reminder, I will be out Wednesday as well due to the same conference. But again, if you need me, send me an email and we will get everything worked out. I'll see y'all Friday.